I had students who had been in my geometry classroom, and 2 years later they were in the calculus classroom. And I found them looking at pictures and diagrams in the calculus textbook and saying, could you make this with Geometry Sketchpad? I want to see this move. And so I found that even if they didn't have Geometry Sketchpad with them as they were talking about that picture, they'd use the language of Geometry Sketchpad. They'd put their fingers in the textbook and start to try to move the points around.
Sketchpad is such a versatile and flexible tool because virtually every academic offering in high school mathematics can make use of it.
I've used it in my pre-calculus class. We used it all year for different things. It's very useful, time saving.
So the way I've used it in my pre-calculus class is I've used a lot of the graphing capabilities, and I've also used more of the locus and geometry capabilities for conic sections. We started the year using it to observe the behavior of the zeros of polynomials of different degree. So what does a zero of degree 1 look like? What does a zero of degree 2 look like? And I do a lot of name that graphs. So like when we studied polynomials, I'd give them a polynomial and say name that graph. And we do that with logarithms. And it's just much easier. I have a projector in my room. I project a graph, hide the function, and they have to come up with it.
Which proves that if you have a ray that comes in perpendicular to the directrix, it's going to bounce through the focus every time. Right? And if you go back to the circle for a second, you'll see the exact same thing. That if I have a ray that comes off the circle, again, these two angles, this angle here and this angle here, that guy and that guy are equal because they're vertical. These guys are equal because it's an isosceles triangle. And so you get angle of incidence equals angle of reflection. A ray from one focus bounces off the ellipse onto the other focus. So it comes out for free. So this is a demo I do to my students. I have other conic section stuff I do where they construct it, but this is a wrap-up I do to the paper folding activity that we do in class to introduce the focal properties of conics.
The trig, we're in the analytical geometry piece, so all the conics are based upon an in-depth discussion with Sketchpad as the main drive. You know, going back to the locus, and then looking at what happens, and then tying into the algebra.
And then we went into the computer lab, and they used Sketchpad to construct a sine wave where the circular motion was one motion, and the movement on a line, the linear motion on the line, was a second motion, and that when the two were joined together, you ended up with the sine curve. I could almost hear light bulbs sort of flashing in the background as they were doing it, because they got very excited and said, "This is why it looks like it is." So they needed something more than just a number basis to really accept the nature of the curve. The dynamic nature of it made a big difference.
Anything in the calculus line, area under the curve, when you increase the number of rectangles and they see that the area is almost identical to the curve. Volumes of revolution blew my school board away. I mean, it was just, oh wow, that's just amazing, amazing stuff.
Okay, for a right endpoint approximation, okay, you've got a lot of symmetry going. I like that. Let's continue on. Or the trapezoid approximation. Looks usually equals that here. That's our height. This is the height. What would the base be? 1/2?
In AP Calculus, it was really useful to, you put a point on a curve, random curve, and then you put a second point that's, like ever so slightly, over, like to the side, on the side of it in order to create a secant. And then being able to adjust how far away that point is from the original point in order to bring that secant point, closer and closer to becoming the tangent. Make that, the slope of that tangent line and the x-coordinate into a point of itself, and then create the locus of that point in order to basically create the derivative function.
Anamorphic street art is a picture that makes it look like this mall is a lily pad. So then I printed this out and brought it with me. And I happen to have a box here that has a pinhole through which we can look and see if it really worked. So, but you can see how this bizarre picture, actually looked at from the right point of view, does give a reasonably realistic image.
That is neat. I have some students who would love that.
This is the Sapinski's gasket, and I wanted to actually play with ways of modifying that. So this one, I said, well, what if it's not divided into thirds?
I had this wonderful student. She was very, very sharp, very, very smart student, but she was a very non-traditional learner. She had a style which was different than what the curriculum demanded. And one day, when we were studying conic sections, she asked the question, in the case of the ellipse, we have two foci which define the ellipse. And she basically asked the question, what if instead of 2 foci, you had 3 foci? And I didn't know the answer for that question myself. But we realized that we had the right technologies to pose the question. So with the help of Sketchpad, we were able to actually visualize these constructs. And what she found out later, that these questions were originally posed by a 19th century mathematician with the name of Kempe, who was very famous for graph theory. And at the time he came to the point of, he defined them, he wrote the equations and so forth, but he could not visualize them because he did not have the means to do so. We were able to finally do something that came to a halting place at the 19th century.
The Sketchpad isn't with them all the time, but I think somehow it's with them all the time. They asked for the Geometer Sketchpad so they could really take those ideas inside their head and put them out there in the outside world for examination and discussion.